All right, the next and really final set of functions that we need to learn how to differentiate and integrate are the inverse trigonometric functions. Now, you should have experience with inverse trigonometric functions from trigonometry. In my experience, students' trigonometry skills are usually not as good as they should be. So if you're in that boat, you're probably going to need some review of inverse trigonometric functions, and I've included a link in our course that gives you the basics of inverse trigonometric functions, from defining them to evaluating them to graphing them, etc. So if you need to, I highly suggest you check out that video. I'll give you a real quick overview right now, but that probably will not be enough for some of you, so I highly suggest you go back and watch that video. Okay, so first off, we're talking about inverse trigonometric functions. I have the statement right here, which seems to contradict what we're going to be doing, which says that none of the 6 trigonometric functions has an inverse. And in some ways that is true, but it's a little misleading in that if we get a little bit clearer there and say, over their entire domain, none of the 6 basic trigonometric functions has an inverse. Okay? And this kind of gets to the crux of the matter, which is what makes inverse trigonometric functions so difficult in some ways, is that we have to look at limiting the domain, and therefore then sometimes that happens to limit the range of the trigonometric functions so that they will have an inverse. You should have a basic understanding of what inverses are and trigonometric functions are. And so the idea is a function will match each value in the domain to exactly one value in the range, and the inverse just goes then back again and matches each element in the range back to one element in the domain of the original function. So, quick little overview. If we look at the sine function, and the sine function is this wave, it's not a one-to-one function, and therefore doesn't have an inverse, because it doesn't pass that horizontal line test that you learned about when you talked about inverses. So what we have to do is we have to cut this function and only look at a piece of the function. So if I look at it in this window, which we have broken out here, that piece between minus pi halves and plus pi halves does have an inverse because it is one-to-one, and the inverse graphically would look like this. And the way you always come up with the inverse graph is if you switch the x's and y's. If AB is on the graph of one function, then BA is on the graph of the inverse. You just swap the x's and the y's, and that's how you can build the graph of the inverse. But we have to cut down the domain and range of the original function. And then that's going to affect the domain and range of the inverse because they reverse themselves. So what we have here for the inverse sine, and we use this arc sine notation. Another notation we could use would be sine with a little -1 as what looks like an exponent but is not an exponent. That's just purely an inverse notation. If we were going to do sine to the -1, it would just be reciprocal of sine, and we would use cosecant. So this -1 never represents an exponent. That would always represent a inverse notation. And this is another way. I prefer the arc notation, but you should be familiar with both and be able to use both. And you'll see both. Okay? So that arc sine now has a domain of -1 to 1 and a range of minus pi halves to plus pi halves. And this will affect what we can plug in and the answers that will come out. Cosine, we do the same thing. We cut the domain, look at just this piece of the cosine function, which I have broken out here. And then the inverse would then look like this. The domain of the arc cosine is -1 to 1, similar to sine, but the range is different. It's 0 to pi. Again, because of the way we have to cut the original function. For the other 4 trigonometric functions, I just jump straight to what the graphs of the inverses will look like. Arctan is here. If you notice, it's got 2 horizontal asymptotes at minus pi halves and plus pi halves. So the domain is actually negative infinity to positive infinity for arctan. And the range, though, is between negative pi halves and plus pi halves. So what happens is x goes to infinity, the y value is going to get closer and closer to positive pi halves. And on the opposite side, as x goes to negative infinity, the y gets closer and closer to negative pi halves. So you should be somewhat familiar with this arctan graph. Here you got arc cotan, here you have arc secant, and here you have arc cosecant. Notice the domain and ranges for each. Now, one thing you should understand is that the reason why these domain and ranges are so important is if we were to evaluate any of these functions, we have to know what we can and cannot plug into each one and what kind of answers would come out. So, if I was to say, what is the arc sine of 7, you would have to realize that the domain of the arc sine is -1 to 1. 7 is not in that domain. So therefore, I can't come up with an answer for arc sine of 7. It doesn't exist. So that's one piece. Another thing is, what if I said, how about the arc sine of a half? Well, a half is in the domain for arc sine. So then the question is, all right, well, what's the answer? Well, you have to realize that this question is pretty much the analogous of this question. The sine of what angle equals a half? And so you're looking for that angle. Now, the problem with that question is that there's a lot of thetas for which the sine equals a half. And this is where the range comes in. The range for the arc sine is negative pi halves to positive pi halves. So the only angles that we can look for which the sine is equal to a half would be those angles that are between minus pi halves and positive pi halves. And so what we would come up with is that the answer is pi sixth, because that's the only angle between negative pi halves and positive pi halves for which the sine is a half. Now this requires you, again, to know your basic trigonometric functions, to know this concept of inverse trigonometric functions, and if you do need review on this stuff, you should go back and review both trig functions and inverse trig functions. Again, I provide a video there for the inverse trig functions, which you can then also look at other videos that I have as they relate to trigonometric functions. The good news is, for what we're going to do in the near term, a lot of this is not necessarily going to be used, in that we're really going to learn how to differentiate these functions. So just to learn how to differentiate these functions, you're not going to need these pieces down pat right now, but you will need them. I mean, there will be a time where we do have to evaluate these functions, understand what the graphs look like, take the limit of these functions, etc. And so you do need to have this stuff down, but in the near future, where we're just talking about taking the derivative of these functions, to learn how to differentiate these functions, this will not necessarily be vital to that, but you will need to know it. If we ever have to evaluate after we take the derivative, or before we take the derivative, or when it comes to integration, same idea. So not to say that you should not review this. You very well should and should know it fairly soon, but to get through the idea of how we take derivatives, we have some time to work on this. So here are our 6 inverse trigonometric functions and their associated derivatives. And so I left them all in the chain rule form, in that I just left this as a u, and u is just some function of x. So that, the more likely scenario would you would not see, say, like the arc sine of just x that you have to take the derivative of, but most likely you'll see, after the first example or two, the arc sine of 3x squared plus 2x plus 1, which is now the arc sine of a function of x, in which case here's your u. Okay, so if we look at each one of these, you look at the arc sine of u. It says it should be u prime over the square root of 1 minus u squared. Again, that u prime is just the derivative of the inside, so that's the chain rule component there. The arctan of u is u prime over 1 plus u squared. The arcsecant of u is u prime over the absolute value of u times the square root of u squared minus 1. And one thing you see is that this column here, arc cosine, arc cotangent, arc cosecant, is just the negative of each one of these. So you should see that pattern right there. Okay? So while there are 6 inverse trigonometric functions, you really don't need to remember 6 brand new derivative rules. You really only have to remember 3 and remember the relationship of how these other ones are just the negative of that. Now, let's take a closer look. This is the arc sine, and this is the arc cosine. Arc tangent, arc cotangent, arc secant, arc cosecant. If you notice, these are the co-functions. Cosine, cotangent, cosecant, sine, tangent, secant on this side. So the co-function for each one is the negative. So if you memorize these 3, you should be able to do these 3. Now, where do these derivative rules come from? Well, the easiest way to show you where these derivative rules come from is to use implicit differentiation. We could use, say, like the limit derivative, the limit definition for derivative, and try and go from real basic form to define these. But the easiest way to do it would be implicit differentiation. And to be honest, you probably saw some of this in Calc 1 with 1, your teacher not telling you what you were actually doing, and 2, not needing to know what you were actually doing. Okay, so let's just do arc sine. Okay, I'll define how we get the arc sine one, and then the rest of them basically fall out the exact same way. So, rather than continue on with that, we'll start doing examples of using these derivative rules. Okay, so let's look at the arc sine. So if I said y equals the arc sine of just x, right? Let's keep it simple. Let's not do a function of x, let's just do x itself. What I'm looking for is what y prime equals, which would be the derivative of the arc sine. Now again, this tells me what I should do, and by using that derivative rule, x being my u, the derivative of x would be 1 over the square root of 1 minus u, which in this case is x squared. That's what the derivative should look like. Okay? But how do we get there? Again, implicit differentiation. So first thing is you got to realize that this statement is the same thing as this statement. Okay? Get rid of the arc sine by taking the sine of both sides of the equation. The sine of y equals x is analogous to y equals the arc sine of x. All right, now that we have that, now what we're going to do is we're going to take the derivative with respect to x of both sides of this equation. Now the reason why we did this is because we know how to take the derivative of the sine function. We're going to use that to help us find what the derivative of the arc sine function is. So to get over here. So in this case, if I take the derivative with respect to x of sine y, that's where your implicit differentiation comes into play, because you're differentiating with respect to x, but the function is a function of y. But remember, y is a function of x, right? So, in essence, you still could take the derivative with respect to x, you just have to do it implicitly. So the way we're going to do that is, if we use implicit differentiation, you should remember that it's basically the chain rule. We take the derivative of the outside, derivative of sine would be cosine. We leave the inside unchanged, and then we multiply by the derivative of the inside, which in this case would be y prime. Well, the other side, we're taking the derivative with respect to x, and it's of just x, and that's just going to give me 1. And so remember, we're looking for y prime. So if we take this equation and we solve for y prime, we would have to divide cosine to the other side. So we get y prime equals 1 over cosine y. So y prime, if y was arc sine x, y prime should be 1 over cosine y. But that's not what we have here. We're saying it should be 1 over square root of 1 minus x squared. So where does that come from? Well, simple. It's a little bit of, math trickery, basic algebra, using some trig identities. We can get there. Because we would like to write the answer as a function of x, right? Y was a function of x, so the derivative of that should be a function of x, would be nice. So we got to kind of mess around with this and get it to that point. Right now it's a function of y. And so the way we do that is a couple of things. One, we're going to use this identity, that sine squared theta plus cosine squared theta equals 1. That's our Pythagorean identity, which is the same thing as saying the cosine of theta equals the square root of 1 minus sine squared theta. Okay? So I could take this denominator, I can write it 1 over the square root of 1 minus sine squared y. Okay? But up here we said that the sine of y equals x. So sine squared y should equal x squared. So we get 1 over the square root of 1 minus x squared. And there's your y prime. That's where this comes from. And so the derivative of the arc sine, as a rule, is 1 over the square root of 1 minus x squared. Or if we try and then further that by the chain rule, if we did the arc sine of u, it would be 1 over the square root of 1 minus u squared times u primes, which is so the u prime in the numerator, and then there's our answer. And all these other ones would come about all for the same reason. We would start off with the function, we'd take the flip the equation around, do implicit differentiation, a little bit of trig identity work to rewrite it, and we get our answer. So now what we really need to do is be able to use these derivatives. So by this point in your calculus career, you realize that derivatives are far easier than integrals. And in order to take a derivative, all you need to know is, what's the rule? How do I do it? And as long as I know what the rule is, I should apply the rule and I get my answer. Probably the hardest part of this whole thing is simplifying in the long run, but the differentiation part, as long as I know what the rule is, should be easy. And that's the case here. So let's say we want to take the derivative of arc sine of x squared. As long as we know the derivative rule, in this case u is x squared, should be really easy. So my derivative should be the derivative of x squared, which is 2x, over the square root of 1 minus x squared squared. Again, this is my u. So if I place that here and here, in that the derivative goes here and the function itself goes there, there's my answer. I do a little simplifying. Pretty easy on this one. 2x over the square root of 1 minus x to the 4th. And that's it. Again, can't get much easier as long as you know the rule. And that's something you're going to want to work on, memorizing these rules. I can't say it enough. I think flashcards are your best bet. They'll be your best friend through Calc 2, Calc 3, differential equations, and every other class where you need to work with derivatives. All right, here's another one, arctangent. So we got to familiarize ourselves with the derivative of the arctan. Again, if it was arctan of a function of x, we'll call that u. It should be u prime over 1 plus u squared. So this is my u. My u is 3x plus 2. So if I'm going to take the derivative of f prime should be 3, which is the derivative of 3x plus 2, over 1 plus 3x plus 2 squared. And that's a derivative. Again, can't get much easier than that. Now, that's not the way we're going to write the final answer, because there's always simplifying we're going to need to do, and that's what's going to take more time than anything. In this case, we'd have to square this. When you square a binomial, make sure you can do that. It would be 9x squared plus 12x plus 4, in which case we would get 3 over 9x squared plus 12x plus 5. So there is our derivative. I'm just going to give you this note real quick. It's going to mean nothing to you right now, but look at this. The derivative of an arctan equaled some constant over a quadratic trinomial. So if I said, no, 2 over 7x squared plus 12x minus 8, that could possibly, not guaranteed, could possibly be the derivative that came from the arctan of something. Just saying, okay? So there's no reason why I'm going to tell you that right now. It does nothing for you. It probably just complicates things a little bit. Just keep that in the back of your brain, because when we get to integrals, it could be helpful. Okay, we go to arc cosine, and remember, cosine is the cofunction for sine, and therefore the inverse arc for arc cosine, the derivative for inverse arc cosine, or the derivative of arc cosine is the negative of what the sine derivative was. And so here's our u. And if you need to kind of take this out and say, okay, how do we take the derivative of square root of x minus 1, because we're going to need that. You can just do that real quick as some scratch work. Remember, that's the 1/2 power. This is the same thing as saying x minus 1 to the 1/2 power. So the derivative would be 1/2 x minus 1 to the minus 1/2 times the derivative inside would just be 1. All right, so keep that in mind. If I'm going to now do the derivative for arc cosine of that square root, it should be 1/2 times x minus 1 to the minus 1/2 over the square root of 1 minus square root of x minus 1 squared. Now, we're going to have to simplify this, but that's your derivative. So here we have a square root squared, so that's going to simplify. Here we have a negative exponent, so it's going to move to the denominator. So I'm going to have 1 over, this 2 is in the denominator. This is a negative exponent, so I'll move that to the denominator. Now it's positive exponent, and this would give me the square root of 1 minus square root squared would give me x minus 1. Well, I really shouldn't have square roots and exponents and fractional exponents in the same answer, so I'll choose one. I'll go with roots as my answer because the original problem had roots. So 2 square root of x minus 1. And here's another square root, which if I distribute this negative would be 2 minus x. They're multiplied because they were multiplied, but I put them all underneath the same square root. There's my answer. Okay, here's your arc secant. This is your u that's inside the arc secant function. This tells me I need to do u prime over the absolute value of u times the square root of u squared minus 1. So this is my u. Knowing what the derivative of that should be in my numerator. And the denominator should have the absolute value of e to the x squared times the square root of e to the x squared squared minus 1. So what's the derivative of this? Well, you always rewrite the exponential function, and then you multiply by the derivative of the exponent. Pretty simple. So now it's a matter of simplifying. There's your derivative. Now all you have to do is simplify it. One thing you need to understand is that the absolute value here is unnecessary. The reason why it's unnecessary is e to the x squared is always positive for all x's. So the absolute value would do nothing. So we can remove those absolute values. That's not always the case. Like if I did the absolute value of, say, sine x, That absolute value is important because the sine of some angles is positive and the sine of other angles is negative, so the absolute value would make a difference depending on what x's we use. That's not the case for e to the x squared. So what I can now do is, since the absolute value is not there, I can cancel this function and this function. If I square this, it's a power to a power, so I multiply those two exponents together. And so my derivative should be simplified to just 2x over the square root of e to the 2x squared minus 1. Again, I multiply these. X squared times 2. All right, so now we have a final example here. I mean, the example is just going to keep looking the same over and over and over again. So I think I've given you enough examples after this one. You should start working with them on your own. This one's a pretty easy one as far as derivatives go. The tricky one about this one is the simplification, which is this problem you've probably been having since Calc 1 is you make your mistakes on the simplifying steps, not so much on the derivative steps. At least hopefully by this point that's the case. And hopefully you're not making as many mistakes on the simplifying either. So if we go to take the derivative, since they're added together, I can do this function separate from this function. So the derivative of the arc sine of x is 1 over the square root of 1 minus x squared plus. In order to take the derivative of this function, it's a product, and I need to use the product rule. So I have x, and I have the square root. So the derivative of x would be 1, and I'll write the square root of 1 minus x squared plus x times, now I got to do the derivative of square root of 1 minus x squared. Well, obviously I would write that as 1 minus x squared to the 1/2. So if I'm going to do the derivative, I would use chain rule, so 1/2. Now the new exponent is minus 1/2, 1 minus x squared, and then I multiply by the derivative of the inside, which would be minus 2x. All right, right there, that's our derivative, right? The differentiation step is now done. We have a lot more work to do in simplifying this, but we're done taking the derivative. It doesn't look nice at all. We're going to try and make it look a little nicer. So, first thing I'm going to do is I'm going to mess around with this. Right off the bat, I'm going to cancel that 1/2 and the 2. These two x's can be multiplied together. I do have a negative I got to make sure I keep track of, and this is going to come to the denominator. So here's where we are. Y prime equals 1 over the square root of 1 minus x squared plus the square root of 1 minus x squared minus, again minus because of this minus here, x squared over the square root of 1 minus x squared. Now remember, if this comes to the denominator, it's now a positive 1/2, and a positive 1/2 is the square root. So I chose to write it as a square root because I have these other ones here as well. Notice these two have the same denominator, so they're real easy to put together. So I'm going to get 1 minus x squared all over the square root of 1 minus x squared plus the square root of 1 minus x squared. Now I can simplify this fraction. There's a couple ways I can do this, but I'm going to do it this way. 1 minus x squared is raised to the first power. Here, 1 minus x squared is really raised to the 1/2 power because of that square root. Well, notice this base and this base are the same. Since they're divided, I should subtract their exponents, which would give me 1 minus x squared to the 1/2. Plus, I still have this other one, which if you want, we could write this as 1 minus x squared to the 1/2, or I could leave it as the square root. Now, these are exactly the same, and if I'm adding them, I have 2 of them. So I have 2 times 1 minus x squared to the 1/2. I could leave the answer like that because there's really not much else I can do with it. That's y prime. Or I could write it as 2 times the square root of 1 minus x squared. Either way, that's the simplified version of our answer, which looks a heck of a lot nicer than all this. but nonetheless, they really are one and the same. This is the derivative. This is the better version of the derivative. The differentiation part was not hard. The simplification part took the longest time, which is typical when it comes to derivatives. Okay, so at this point, I know we've done this before, but now here is a complete list of all the functions, or let's say all the rules that you should know for differentiation by this point in Calculus 2. And honestly, moving forward, we're not really adding anything to this list, so this is it. Okay, the only other functions that are not on this list would be the hyperbolic trigonometric functions. So we're not there. We're not going to get to cover that this semester, mainly just due to time. It's one of those things that just doesn't get covered sometimes in a Calculus 2 course. But generally, this is it. This is your list. So we've gone through a lot of these. You could pause the video and you can sit there and look at them and make sure you know which ones you know, which ones you don't know. And the ones you don't know, maybe write them down. Obviously, there's going to be a group here that we just learned, so they're not going to be as fresh in your head. But you should know this basic list of functions and their derivatives. So these are the derivative rules you should know. And if you have all these down, these 24 different derivative rules, I would say make an index card for each one. Put this on the front, put this on the back, quiz yourself over and over and over again, and you should have these things memorized. It will make your life easier if you do so in the future. For those of you who refuse to remember any of these things, you're just going to constantly struggle. So if you want to make your life easier moving forward, I would go ahead and get these things down.